Okay, so this week we are going to study some more advanced one for MS metal semiconductor context. So before moving forward, let's briefly review what we have learned last week. So last week we have learned there are two different types of MS contacts, one of which is a rectifying contact or named as, so to speak, a Schottky diode. So in this case, for a given forward bias, I mean the positive bias on the metal side, negative bias on the semiconductor side, uh, the, the current flow is exponentially increasing as the voltage difference between metal and semiconductor is increasing at a linear pace. However, once the metal semiconductor voltage difference is negative, in other words, a reverse bias is applied onto the MS or a Schottky diode, then the total amount of current flow throughout the Schottky diode is very minimal, negligible. So unidirectional current flow can be achieved and implemented in Schottky diode. That is the reason why we are saying that this is a diode. Okay, the basic role of diode is to rectify or direct the current in which direction the current is flowing in a diode. Okay, then the second type of the MS contact was defined as non-rectifying contact, or named as, so to speak, ohmic contact. So basically, if your MS contact has a function of ohmic contact, it is it is all very similar to the like a single tiny piece of silicon material. In other words, if your MS contact has the function of ohmic contact, your MS contact is, simply speaking, a resistor. Okay, so once a positive bias is applied onto the metal side, then a positively directed current flow can be formed. And if the negative voltage is applied onto the metal side, the negatively directed current flow can be obtained throughout the ohmic contact or MS contact. Therefore, it is almost like a resistor. So you may draw the current versus voltage plot for each case. Just for your information, if I draw the current versus voltage characteristic of Schottky diode, then you're gonna get this curve shape. But in for the ohmic contact case, its current versus voltage characteristic would be this. Okay, so just for your information here, metal semiconductor contact has been formed, the source side is referenced, and the voltage is applied on the metal side, and current is defined as from metal to semiconductor. So last week we have deeply analyzed how to draw the energy band diagram once the metal is contacted with the n-type semiconductor. And depending on the work function difference between metal and n-type semiconductor, we can classify two different MS contexts, one of which is rectifying or Schottky diode, which is shown in this slide. And on the bottom right hand side, you can see the energy band diagram at thermal equilibrium for ideal MS contact where metal work function is higher than the semiconductor's work function. However, in this slide, as shown in this slide, uh, the metal work function is lower than the n-type semiconductor's work function, then we're gonna get the ohmic contact. And at equilibrium, at thermal equilibrium, you may see the energy band diagram as shown in here. So you can clearly see that many electrons would move back and forth without any energy barrier height. Of course, there is a small, very energy barrier. That is the main reason why, if you have any chance to measure the IV characteristic of this ohmic contact MS contact, uh, in this direction, the current is linearly increasing as voltage is increasing linearly. However, on the reverse side, instead of expecting the straight line at this very small negative or reverse bias, presume the current is not flowing well, but in the end, it's going to follow the straight line. So here, small hump would be measured in OMI contact, MS, OMI contact or MS contact. No. In OMI contact, okay? All right. And as shown in this slide, you can see that let me see. Yeah. Once a semiconductor side is a p-type semiconductor, then um, the everything is upside down. So previously we put our eyes onto the conduction band, how those free electrons are moving back and forth throughout the MS diode. However, in this case, we should put our attention onto the holes in the balance band. So if you put your attention how those holes are moving in balance band, you may see that from the perspective of this hole can see the energy barrier height. Why is that? Again, the minus y-axis indicates the energy of hole, okay? And plus y direction is matched to the energy of free electron, okay? So everything is same, right? But other than, energy band diagram is upside down, okay? All right, so I guess uh, you should train yourself how to draw the energy band diagram for any combination of MS, okay? All right, and let me see. In the next slide, let me see. Yeah, yeah, there we go. So previously we mentioned that ideal MS contact. From now on, let's keep an eye on what any non-ideality happened in interface between matter and semiconductor. Can you imagine any non-ideality in between matter and semiconductor? Can you guess what else you can imagine to be existing at the interface between matter and semiconductor? In the case of ideal MS contact, there is no defect, no mismatch between matter atoms and the silicon atoms. We have already assumed in ideal MS diode, we have already assumed that the matter atom is well aligned and matched and combined and bonded with the silicon atoms which are sitting onto the top surface of the semiconductor. So I'm talking about here. Let me see, where's my pen? Okay. So here, matter and semiconductor. I'm talking about this physical interface. There is a matter atom and silicon atom. Do you agree to the? Do you think these matter and silicon atoms are well bonded without any defect? Well, depending on the atomic size of matter, do you think that matter atomic size is really identical to the silicon atomic size? I mean, the silicon atom size is perfectly matched to the physical dimension or size of the matter atom? Maybe not, right? Therefore, we should expect some, you know, some defect, not perfect. So imperfect interface surface are really expected. Then in energy band diagram, how to express them? That's a good question, right? So many solid state physicists has studied how to draw the energy band diagram, including the impact of interface traps or defects between MS. That was old long it has this kind of question has a long history, and many researchers has investigated many tons of experiments and theoretical studies, and it turned out that uh, we cannot remove completely all the defects between at the interface between matter and semiconductor, but we can alleviate. I mean that we can uh, put we can have the total amount of interface defects under a certain level or under a certain value. So it turned out that if for a given square centimeter, if the total number of interface defect is below 10 to the 12, again 10 to the 12 per 1 centimeter, then that would be good enough. So theoretical limit is approximately 10 to the 10 per 1 square centimeter, but it's very tough and it is not very cost effective. So in industry, process engineer would control and monitor in real time the total amount of interface states below 10 to the 12 per 1 centimeter. Then that's good enough. Okay. So that is just for your information. And now let's go back to the energy band diagram, how to draw the interface states. So that's very simple. As we have learned in bulk silicon, right? In in between EC and EV, there is no energy state, right? However, between matter and semiconductor, because of the interface traps, there are many newly created energy states available. So these states and energy levels are not available in the bulk silicon region of MS contact, only available at the interface. Okay. Then the question is, in ideal MS contact, the Schottky barrier height, pi sub Bn here, was defined as metal work function minus electron affinity of silicon side, chi silicon, right? So that was very simple, and this Schottky barrier height has been determined by, or function of matter side and electron affinity, which is the material parameter, which we cannot modify it. Once we are using the silicon material, there is no option to modify the electron affinity of silicon. However, that is all for the ideal MS contact. But in real MS contact, as described here, a high density of loud energy states in the bandgap at the interface. Again here, a high density of loud energy. Loud energy means the electron can take into this energy state where in the bandgap at MS interface. So the authors of your textbook are talking about these energy states. Okay, and he said high density. That means many. How many? About 10 to the 12 to 13 per square centimeter. Okay, so if I draw the three-dimensionally the MS diode, so think about this cross-sectional area. Okay, this area is a few in the unit of square centimeter. Then okay, um, you may guess how many interface states are available. Then the next one is here, pins. Okay, these allowed energy states. In other words, those newly created energy states available in the bandgap can pin. Pin means a set what? Set Fermi energy level. Where? In the range of zero point 0.4 electron to zero point 0.9 electron volt below E sub C. So let me raise my note and let's see. Yeah, from EC level below 0.4 or 0.9. So in this regime, okay, Fermi energy level would be pinned. That means set. So in this case, EF has been set at this specific energy state. Previously, according to the ideal MS contact theory, the Fermi energy level of matter and Fermi energy level for semiconductor, those are misaligned when they are separated physically. However, once matter is physically contacted to the n-type silicon material, the misaligned Fermi energy level should be aligned to each other at thermal equilibrium. So in that process of aligning two different Fermi energy level of matter and semiconductor, the band bending can be happened near the interface. So now we are taking a look at the completed and stabilized energy band diagram at thermal equilibrium. So Schottky barrier height has been well formed. Uh, when we have learned the ideal MS contact theory, EFM, EFS difference has been determined by the work function difference, right? So Fermi energy level, the energy difference between Fermi energy level and vacuum energy level has been defined as a work function. So if we are claiming that Fermi energy level of matter is very different from the Fermi energy level of semiconductor, then it is equally speaking, the work function of matter is very different from the work function of semiconductor. But once those two materials, matter and semiconductors, are physically contacted, because it is now combined into a single system, the Fermi energy level of matter and semiconductor should be aligned well. But the problem is the interface states are still there, still exist. So more technically speaking, the MS, instead of saying MS contact, now we are saying the M interface semiconductor. So three different stuff are combined together as a single system. Okay, so in that sense, you may guess and figure out or the concept why the Fermi energy level in real MS contact, not in ideal MS contact. In real MS contact, how come the Fermi energy level has been pinned in the energy band diagram? Usually, in general, below conduction band energy level, zero 0.4 electron volt to 0.9 electron volt. That is a main regime where you can find the Fermi energy level for real MS contact. So many researchers has studied how to modify and how to control the position of the pinned Fermi energy level. There are many research papers uh, in the last few decades, and people has found that we may have many options to use options for metal side, erbium, titanium, nickel, tungsten, molybdenum, stuff, and so on. So depending on the type of matter, the matter work function is definitely different. And depending on the matter work function, or depending on the your choice of matter, the Schottky barrier height would be very different. So they have observed that Schottky barrier height, so in this case, MS n-type semiconductor, MS contact, Schottky barrier height tends to increase with increasing metal work function. So as you can see here, if metal work function is increasing, the pi sub Bn Schottky barrier height is increasing, but not exactly. Okay, so in the ideal MS diode theory, phi m minus phi s is defined as a Schottky barrier. The no chi is defined as a Schottky barrier height, phi sub Bn. But this the amount of how much matter work function has been varied is not exactly identical to how much Schottky barrier height has been modified. Simply speaking, this equation is not well fit to the real MS diode. So why is that? So many guys has studied that and found that Fermi energy level has been pinned because of the interface states between matter and semiconductor. So many engineers has put their times and efforts how to control the Schottky barrier height in real MS diode, uh, they found and suggest and proposed new technique named as silicidation. So silicide on silicon. So what that means is, matter itself can be physically deposited onto the silicon surface. However, if we anneal, if we heat up the wafer with the deposited metal material, then at the interface between metal and semiconductor, the silicided material can be newly created. So the once the matter is physically deposited onto the silicon, matter is still matter, the same, no change, no chemical reaction has been happened. But if we heat up the wafer, then the matter can be chemically reacted with the silicon atom. In the end, at the interface or near the interface, the new material named as a silicide material can be formed. So for example, erbium is combined with a silicon chemically, then erbium silicon material has been newly created. Then this erbium silicide silicon is very different material from erbium itself and silicon itself. Therefore, the matter of function of erbium silicide or the work function of silicided material is very quite different from the work function of silicon, work function of matter, pure matter itself. Okay, so many researchers has found that erbium silicide, thisilicide, and Nisi, this is the mainstream currently used in CMOS technology platform, and the tungsten disilicide is an emerging one, and cobalt silicide disilicon is another new option. Maybe within 5 years, industries would like to adopt cobalt material as contact material or even better one. So it depends on the company. And silicide silicon or the siliciding technique has been well adopted. So why? What is the physical origin and what is the main advantage of adopting silicidation technique between metal and semiconductor? The answer can be found at the very first sentence here. Silicide silicon interfaces are more stable, much more stable than what? Metal silicon interface itself. So uh, simply depositing the metal material onto the semiconductor cannot make sure the good quality, good interface quality between metal and semiconductor. However, once the metal is physically deposited onto the silicon surface, and if we can heat up the wafer, then a chemical reaction can be induced, resulting in a silicided material at the interface, so that very stabilized silicide silicon interface can be obtained. Okay, so as described on the second sentence, after matter is deposited onto silicon, a thermal annealing step is applied for what? Yeah, to form a silicide silicon contact instead of metal silicon contact itself. The term metal silicon contact includes what? Silicide silicon contact. So from now on, I'm going to say metal silicon contact, including silicide silicon contact. But in industry, whenever industry guy is talking about metal silicon contact, always they are thinking of silicide silicon contacts. The physically, purely, and without any chemically reacted metal silicon contact can never be used in industry. Always they are using a silicide silicon contact. Okay, so I guess that's for the general, comments how to understand interface states between metal and semiconductor. Okay, so from this slide, some more quantitative analysis has been introduced. So I guess it's a good time to have a short break time here. And please have your own time to preview what the depletion approximation is and what the electrostatics in MS diode and how to develop the equation for depletion layer width in matter than semiconductor context. So please think about this issue, and afterwards, please play my second movie clip for this week. See you.